Welcome to Next Gen Manufacturing. Today, we are diving deep into the synthetic materials that have completely reshaped our modern world. I mean, everything from the car you drive to the smartphone in your hand. So, let's get right into it.
Okay, so this sounds like a random trivia question, right? But believe it or not, this is pretty much where the story of modern plastics kicks off. We have to go all the way back to 1869. Elephant populations were in danger, and there was a real push to find a substitute for ivory. A guy named John Wesley Hyatt entered a competition and came up with something called celluloid. It was one of the very first synthetic polymers, and it lit the fuse on a massive quest to engineer materials with properties you just couldn't find in nature.
You know, for thousands of years, we built things with what we could dig up or chop down, metal, wood, stone, that sort of thing. But those materials, they have their limits. And as we hit the 20th century, we needed more. We needed something that could be engineered from the molecule up.
And here's the fundamental trade-off, right here on the screen. Think about it. Metals are strong, sure, but they're heavy and they rust. Wood is great, but it can rot and warp. And getting either of them into really intricate shapes, that's tough and expensive. Well, synthetic polymers completely flip the script. They're lightweight, they don't corrode, and you can mold them into these incredibly complex, single-piece parts. This ability to integrate functions to make one part do the job of 10 metal pieces absolutely slashed assembly costs. It was a true game changer for manufacturing.
So how do these amazing materials actually work? I mean, what makes them tick? To get that, we need to zoom way in, all the way down to the molecular level. This is the blueprint for all modern polymers. At its core, a polymer is actually a pretty simple idea. Just imagine you have a giant chain made of thousands, even millions of identical paper clips linked end to end. Each one of those paper clips is what we call a monomer. The whole chain, that's the polymer. And everything about the final material, is it flexible, is it rigid, is it clear, it all comes down to what kind of monomer you use and how those long chains are arranged.
Now, not all polymers are created equal. They basically fall into two big families. On one side, you have thermoplastics. The easiest way to think of these is like chocolate. You can melt a chocolate bar down, pour it into a new shape, and let it cool. You can do that over and over again. That's because their long molecular chains just kind of slide past each other when they get hot. Then you have thermosets. These are more like bread dough. Once you bake it, that's it. A chemical reaction creates this rigid, cross-linked 3D network. You can't just melt it back down into dough again. This difference is absolutely critical for understanding how these materials are used and, importantly, how they can be recycled. So, polymers are fantastic, but let's be real, on their own, they often just aren't strong enough for the really tough jobs, like critical car parts or airplane components. So, what's the next move? Where do you go from here in this manufacturing evolution?
Well, you create a composite. You take your base polymer, what we call the matrix, and you embed it with super strong reinforcing fibers. It's the same idea as reinforced concrete with its steel rebar, just on a microscopic scale. You're basically supercharging the plastic. Glass fibers are the everyday workhorse here. They're cheap and effective. But for the really high-end stuff, where you need maximum stiffness and minimum weight, you bring in the carbon fiber. And for things that need to take a serious hit, like, say, stopping a bullet, you go with aramid fibers, which you probably know by the brand name Kevlar. Okay, so we've got the blueprint for our materials. But how do we actually turn these powders and pellets into the useful parts we see all around us? This is where the real magic of modern manufacturing happens. When you need to make millions of something, injection molding is absolute king. Think of every Lego brick ever made. You start with these tiny plastic pellets, or granules. You dump them in a hopper, a giant screw melts them down, and then, bam! That molten plastic gets injected into a super precise metal mold under insane pressure. It cools in seconds, the mold pops open, and out comes a perfect part. Then it does it again, and again, and again. Another really common method, especially for bigger, thinner parts, like food packaging or the inside panel of your car door, is thermoforming. It's a pretty clever process. You just take a flat sheet of plastic, heat it up until it gets soft and droopy, and then use a vacuum to suck it down tight against a mold. It's fast, it's efficient, and it's a great way to make large parts without a super complex setup. So picking the right material and the right process, that's only half the battle. For engineers, the real challenge is figuring out exactly how these materials are going to behave out in the real world, under heat, under stress, under all kinds of conditions. It's a really complex performance equation they have to solve. And here is the hard data that shows you why composites are such a big deal. Just look at polyamide 66, a super common engineering plastic.
By itself, its flexion strength maxes out around 125 megapascals. Okay, not bad. But look what happens when you add 30% glass fiber to it. That strength can shoot up to 350 megapascals. That's almost triple. This is how you get a lightweight plastic part that can actually outperform a metal one.
But it's not all easy. There are definitely challenges, and this chart shows a huge one: thermal expansion. See that little bar for steel? It barely moves when it gets hot. Now look at the unreinforced polyamide. Whoa! It expands almost 10 times more than steel for the same temperature change. Now imagine you bolt that plastic part directly to a metal frame. What's going to happen when the sun comes out? The plastic is going to try and expand, but the metal won't let it. It's going to buckle or even crack. Adding those reinforcement fibers, as you can see, helps a lot in controlling this, but it's something engineers always have to account for.
So we've seen how these materials are designed, made, and used. But what about the big question? What happens when we're done with them? The answer to that is defining the entire next chapter for manufacturing.
The industry is really working on closing the loop, and they're attacking the problem from a bunch of different angles. For thermoplastics, our chocolate plastics, mechanical recycling is common. You just grind them up and melt them down to make new things. For thermosets, the baked bread ones, you can't remelt them, but you can grind them into a powder and use it as filler in other materials. And now we're seeing these really advanced methods pop up, like chemical valorization, where you actually break the polymer chains all the way back down into their original monomer building blocks. That is the holy grail for creating a truly circular economy.
You know, we name entire periods of human history after the dominant material of the time. We had the Stone Age, the Bronze Age, the Iron Age. There's no doubt about it, we are living smack dab in the middle of the Polymer Age. These materials that we've engineered from scratch have taken us to the moon and put literal supercomputers in our pockets. So the only real question left is, with materials that we can now design practically atom by atom, what on earth are we going to build next?